All right, hello again. So we are going to do something somewhat similar to what we did with the proportions. So I'm going to pick one of my quantitative variables, and I picked sibling number. And so I looked for some information on Google about number of siblings, and I found this site, which was pretty cool. Had a lot of good data about family size, but there's something a little sus about it. So they're saying their number of own children. So they're not talking about siblings. They're just talking about how many kids in the family. And I think they're going very traditional. No foster, no step, maybe not even adopted kids, and so they're getting this number in the family, which even back in the day meant that there was only an average of, in 1965, only an average of 1.44 siblings. If there's 2.44 kids and 1.44 siblings. So, that doesn't really jive well with what I see in my sibling number. So I ran the describe function again to sort of see some of this data, and we have 2.87 nine, blah blah blah, almost 2.9 siblings, which would make 3.9 kids in the family. So this has to be including more diverse kinds of siblings, which is fine. Um, but what I've kind of done is said, all right, well, let's just run a test to see if the mean number of siblings is greater than that traditional number of kids. So I made my null hypothesis 2.44 based on the 1965 number, and I'm running a right-tailed test to see if there's enough evidence to show that the mean is actually greater than that based on this sample. Excuse me. This is not my first take, so my voice is starting to go away. All right, so I go over here. There's a nice t-test. I have to import something in order for it to run, but it's pretty straightforward. You put, where the data is coming from, the mean in your null hypothesis, and then this time, instead of larger for a right-tailed test when the alternative hypothesis is greater than, we actually have to put greater, which is a little bit easier to remember. And when I run this, man, I get bupkis. So, I think it has to do with the sample size. Typically you're running a t-test because your sample size is less than 30. And so I'm guessing Python just isn't able to handle such a big number. And just to test that really, this isn't just complete gibberish that I'm saying, I went ahead and tried the function on a really small data set to see if it gives me something reasonable. So I just picked a couple of numbers that I know that the mean is 3, because there's just as much in the same distance away from 3 on the left as there is on the right of 3. And so, is this enough of a sample to give evidence that the sample of the population that this came from, what my head, is greater than 2.44, run that, and it does just fine. So might come back to this and show that Python is giving the same numbers that it should, depending on how long this video runs. But what I'm going to do is I'm going to go into Desmos, to our handy dandy t-test calculator, and let it do its dirty work. So I need to get the information, the mu. I think I can remember it's 2.44. But what's the X bar? What's the sample mean? That's 2.879. I wonder if I can get it from my slide a little bit easier. I think I can copy and paste it from here. Yeah. Copy and paste. And then the standard deviation, also from my slide, not from my slide, but from my program. 2.36. Copy and paste. Sample size is 5301. I remember that. All right. So we're getting a really small sampling error. I'm sorry, the really small standard error, the sampling distribution sample size, sampling distribution standard deviation. called the standard error. Pretty darn small, and it's giving 13.5 as the t-statistic. So the number of these standard deviations that 2.879 is from the assumed middle mean 2.44, it's a lot of standard deviations. So when I go and copy this into here, it's already giving the right degrees of freedom. It's taking the n that we put in before and subtracting 1. So this is going to be 5,300 degrees of freedom. But here's that p-value. And this minus 41 means there's 41 zeros. It's 0.0000041 zeros until you get to the 259 stuff. So basically 0. So that's what I put in my slide. If we look at the second one, when we look at the second one, that's what I'm putting here. All right, real quickly, I'm just going to show that Python, using this, is getting the same stuff. So what I'm going to do is, I know the mean here is 3, so I'm going to go back, and I'm still going to use the 2.44 because that's what I used in Python. But that little data set, the mean is 3, and I ran the standard deviation of it, and it's this 1.412 stuff. So we're going to put that in. The n now is just 6, right? 1, 2, 3, 4, 5, 6. Yeah, it's a 6-element list. Okay, cool. Now our standard error, the standard deviation of the sampling distribution, is a little bit more than a half. And so my t-statistic, it's basically one of those standard deviations away. That this 3 is about 1 standard deviation away from 2.44. Okay, so when we do this with that t-value, we get 0.1883 basically for our p-value. So our t-statistic 0.969948. 0.969948, that's our t-statistic, and Python got the same thing. And our p-value 0.1883, degrees of freedom 5. Everything that Python was doing is correct. It wasn't getting an error. We just went beyond its capabilities with our big sample size. Okay, have a great day. I'll talk to you soon. Bye.